Yeah, so it's there's a lot of hype about it. Can people see it from there? Should I move this? Is it okay? No. Okay. So yeah, so there's a lot of hype about it. And what are deep nets? Deep nets, to a first approximation, are like neural nets. Okay. So just a history reminder. So in the 1940s, people discovered neurons, right? That the brain consists of neurons. And what's a neuron? There's this thing, and it has connections to other neurons. And then each of these is like a wire with a weight on it, 0.5, minus 0.7. You know, there's negative weights too, which inhibit, and these are excitatory. And then all the other neurons fire, and then this one decides whether to fire based on the sum of the weights. Okay, there's a threshold function, roughly. So that was the simplistic model, and then based on that, McCulloch and Pitts proposed this learning model called the perceptron, which is just a half space, ax bigger than or equal to b. And your data point is some x, and it's a 1 if, let's say, it's less than or equal to and 0 otherwise. Okay, so it's a simple classifier, a linear classifier. So that's perceptron. And then it took until the 1960s for people to point out that actually a linear classifier is not very expressive, that you can't express a lot of interesting concepts with a linear classifier. Somehow this took until the 1960s. And so that was about perceptrons. And then then after that, people started using neural nets to try to do learning, which I'm sure you saw at some point. So it's just a network of neural nets of these perceptrons. Okay, so there's some a1x is bigger than or equal to b1, a2x is bigger than or equal to b2, etc. Okay, so there's a level of threshold gates. In theoretical computer science, this model is called TC0. Threshold gates, constant number of levels. And so yeah, x is the input. So you have these thresholds which compute a 0, 1 input again for the next layer and so on. Okay, so that's neural nets. So I'm just recounting to you all the stuff that I thought, you know, which you all seen, and like probably all of you, I consider also kind of pseudoscience. Okay, that you just sort of hear about along with, you know, all kinds of other pseudoscience. Okay, so so there's neural nets, and then how do people train neural nets? So there was this backpropagation algorithm, which is something like the perceptron algorithm. Okay, there are multiple versions of backpropagation.
Sanjeev, I think you're mixing two things. One is a model of computation, which is
no, this was all mixed up. That's why I'm mixing it. So I'll disentangle all of them. Yeah, this is history. Yeah, all of this has to be disentangled, and it's not done, right? Okay, so then okay, so the learning problem is how is neural net learning done? So you just assume there's a let's say 3-level neural net. Okay, you just from some first principles thinking about the problem, you say 3 levels sounds good to me, and then you
3 levels means that some concept that's being computed is
no. I'll yeah. So and then the goal of the neural net is something like recognizing characters or speech recognition or whatever, and you don't know what these nodes are going to compute and what their weights are or anything. Okay, you're going to learn that, and so you input your data, processed however you like, and then the output comes out. You start with some arbitrary, say random net or something, and then the data comes out. Sorry, the answer comes out from this current net, and if that answer is wrong, you do backpropagation. Okay, and the backpropagation is roughly like gradient descent, not quite, in a nonlinear framework, and you sort of give feedback to all these weights and make them adjust. Okay, if you think about it for a little bit and look at gradients and so on, you'll come up with the rules, at least the simplest rules. And you adjust the weights, and then see again if it's predicting now, and wherever it's not predicting, you do some more adjustments. Okay, that's That's neural net learning. Okay, that was done in the 80s. Okay, so that's the classical stuff. So this often tended to do well if you have one layer or two layers, but more layers was difficult. Okay, and the reason is that these continuous optimization things, they are very interlinked, and the signal that makes it through this back propagation to this is very, very weak. Okay, so then we come to modern deep nets research, which is not quite that. Okay, it's reminiscent of that, but it's not quite that. So by the way, I should point out, so the theory people, of course, thought about this problem. Okay, so let me tell you what the theory says. Okay, so the bottom line is that it's going to be very, very hard, okay, to learn this. So the theory problem, according to the pack view of Valiant, is that you're learning a classifier which is a neural net. Okay, so multi-levels of threshold gates, and there's some distribution on the inputs, D, and you're given samples from that distribution, and there's this unknown net, and what you're given is the right answer. And then, so the question is to figure out this thing. And this problem theorists have thought about now for 3 decades, and seems very, very difficult. And even the simple case where this is just basically a 2-level network, or 1.5, DNF. Okay, so OR of ANDs, so OR of ANDs. Even that that seems beyond reach. Okay, the best algorithm is like 2 to the root n, the cube root of n time for general distributions. So forget multiple levels of threshold gates. Okay, just DNF is very hard. So the theory is completely stuck here too. So we don't need to be to think that we have any answers here. Okay, so so the modern deep net research. Let me just go here. So what Hinton changed? So Hinton is a professor at Toronto, and now at Google, leading their deep learning research. So he proposed a different approach to neural net. So the difference from here is that this is what's called unsupervised. Sorry, this is called supervised. Okay, supervised in the sense that there's correct answer being given on every input. Now, it's clear that for any interesting task, you will need very large networks, hundreds of thousands of nodes. Okay, and that's what people are trying to do. Like Google is doing this right now, 500,000 nodes, 1 million nodes. So to learn that, just from VC dimension bounds, you need a lot of samples. Okay, just in principle to learn it. Forget about efficient algorithms. And so it was felt that there just aren't enough labeled examples in the world. Okay, so they really wanted to do unsupervised. So that was one motivation for this modern deep net research, that you want unsupervised examples where you're just given, for example, if it's image recognition, just a huge database of images, and maybe there's some labels there, maybe not, and just from that database you learn something like, what's a good image? Okay, what are different types of images? You just sort of learn some kind of clustering classification. Okay, completely unsupervised setting. So can you do that? Okay, so in order to enable this unsupervised view, or even to get it off the ground, what Hinton suggested was that, the way we've been doing deep nets, there's just it's a computational device that transforms inputs to an output, right? So he said, forget about this 1-bit output. Okay, the goal of the neural net is to produce some representation. And this representation is going to be computed by gates kind of like this, although they're not completely insisting that it has to be threshold gates, but something nonlinear. They do want nonlinear. They think nonlinear is important. And what these levels do is they encode the input, okay? But it's hopefully a more clever encoding. Okay, so what does encoding mean? Encoding means that you should be able to invert it. So you can go from X to this encoding H for hidden. And then from this hidden layer, you should be able to generate something like X. Maybe not X, but X plus noise or something. Okay? So in other words, he's suggesting that your computational model is also reversible and is a generative model. Okay, generative model in the sense that machine learning people talk about generative models. You know, you assume that the data is coming from a distribution, like mixtures of Gaussians or topping models or whatever. And you assume a generative model where there's some hidden parameters, and this model is generating your data. Okay, and the goal of learning is to learn the parameters of this model. Okay, so in that sense, okay, so it's a generative model. So this deep, yeah, we have to assume something more. Yeah, so deep net, so it's going to be something like reversible. Okay, roughly that means that you should be not only able to go this way, but also that way, using possibly a different computation. Think of it as decoding. Okay, it's very reminiscent of error correcting codes and decoding. And what was the other thing I was? Oh, it's a generative model. So therefore, hence the net is a generative model. No, the generative model, okay, so generative model is this direction. This is the computation. You transform input into a hidden representation, and this is the generative model.
So what's the distribution of the, we don't know the distribution of the output that is generated.
So that's what so that's what I'll talk about more. So this is all done vaguely. I mean, these are not, you know, mathematical papers. Okay, these are always, you know, in the context of I tried this and I implemented on this what it did on the data. Okay, so you have to, and there are some writers in that field who write quite well, and where you can sort of understand the intuition a little bit better. Like if you want to read up more, Bengio is a very good writer. He has a few surveys. Okay, so I'm just giving you the overall idea, and the details can differ. Okay, exactly what that means. But the idea is that this net that you're learning with its various parameters, those are also parameters of the generative model. And so, for instance, if they are learning, for instance, digits, handwriting recognition, okay, this was an early success. The Postal Service, you know, uses that software to like read zip codes and so on. So indeed, when you run that generative model, you get things that look kind of like digits, okay, in all kinds of, with all kinds of warping and orientation and so on.
You start with just the digit 0, and then you send it through this generative model, and you get some handwritten looking.
No. So the model is trained using millions of examples of handwritten digits, and then it learns something, and then if you generate that, you get these blurry images which look kind of like blurry because they are kind of noisy versions of digits written all kinds of ways.
So that's what Andy said. He said after you learn this, when you start with a 0 in the output, you'll get a blurry image of
No,
0.
you don't start with a 0 in the output.
What do you start with in the output?
So you get a distribution in the output as well.
Where is the kurtosis coefficient? I mean, at some point you have to decide that this is 0, this is 1.
Good. Okay, so let's go on. Okay, so yeah. So then you get this generative model. So there's a few questions, right? Firstly, why can't this circuit just compute identity, right? Well, it can't do identity per se because, they impose some kind of constraints. So for instance, these layers are bigger, but the number of ones is small. Okay, so it's a sparse representation, for instance. So it's kind of like compressed sensing or something. Okay, some of those kinds of ideas. And then the supervised part. So you can train on millions of data points unsupervised. Okay, and you get some kind of representation of your distribution. And because of the other constraints imposed, it's not identity. And then you train using supervised. So you have 10,000 examples of labeled digits, and you train it. Okay, and during that training, you may actually change these weights some more. So this unsupervised part is a setup for a bit of supervised training at the end.
So can you tell this same story instead of in general about the post office and the digits? Just the same, what's going on when somebody thinks about, I want to have an automatic recognizer of digits. And then they start using this methodology. So what do they do exactly?
Okay, so so what do they do beyond what I just said? You want more details?
How did they develop the software? They had nothing. They only knew that they wished the post office.
Okay, so there's a lot of art, as you would imagine. Okay, so what functions do you use here to optimize? So it's all. So by the way, if you don't know this, machine learning, 95% of it is basically just you come up with a model and then you do nonlinear optimization. Okay. Not something that we theorists would think about. So you have some crazy function, like this thing that it's a generative model. You could have some penalty function over all the samples. If this is the encoding direction and this is the decoding direction, you might have something like encoding of x plus noise. Sorry. Decoding of encoding of x plus noise minus x square, okay? Something like that, if you are using a square loss, but you could use other loss functions. So you have some objective like that, okay? And this is already nonlinear, okay? This inside it. This is unsupervised, where you're just saying that the distribution. Oh no, x is the sample. This sample.
So I think what they're trying to ask is, once you learn the representation, how do you do the digit classification? I think
How do you do the
classification for the digits with the
Okay. So in general, this viewpoint comes from SVMs and other branches of machine learning, that once you have the whole point is to learn a better representation of the data. That your data is in some very poor representation. You learn a better representation, and then you do some simple classifier on that representation, like perceptrons, okay, or SVMs.
At some point, they need labeled examples, right?
Yeah.
Okay.
That's what I was saying here. This. So that's what I was saying. Yeah, there's a supervised stage using this representation, and then that does provide feedback to this, and you may improve during that stage this a bit too.
So so I don't see the answer to my question.
Okay.
They wanted to develop software for digit recognition.
Yeah.
They picked, let's say, neural net of size
Something and depth 3.
and depth 5.
Yeah.
They chose it.
Yeah.
And then they took images of the different digits in the
Yeah.
the people's letters.
Yeah.
Fed them through this.
Yeah.
And then what did they do later?
Okay. So then they learn a representation, the top layer. Okay. And then they run, let's say, perceptron. Okay. Not necessarily perceptron, but something like that. Okay. A simple classifier.
When you say they learn the representation,
On this, so there's a set of bits which represent each digit, right?
it's not
Each
clear
sum.
because, I'm not sure what you mean learned even there, because different digits have different. So they ran
That's the whole point. That's the whole point.
They ran it
For each sample point. So for each sample point, you get a representation.
So they did something like this.
Yeah. No, this is to learn the network. So, yeah.
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 I'm talking about one step at a time, learning the network. So in order to learn the network, they run this kind of
Nonlinear optimization.
nonlinear optimization.
Yeah.
Okay.
Which is just done via gradient descent or somewhat more sophisticated versions of that. Okay, so this function is nonlinear, and you have the samples, okay, your million samples. So the sum over all those terms, nonlinear term. You do gradient descent, stochastic gradient descent, whatever.
And they constrained it so it would not be identical.
Yeah. Yes.
Is the representation usually much smaller than the input?
Not clear. Yeah. Yes, it should be smaller, right? Because you shouldn't add information, right, than what you have. So yes, generally it should be smaller.
So
Yeah.
something like PCA is basically doing this in a very simple way.
Yeah, PCA is a very trivial subcase of this, yes, and not a very useful one. Yeah. They think that you should use some nonlinearity. That's right. So PCA, compressed sensing, these are all sort of linear subcases of this. Okay? Any other questions?
So just to finish the story, after they learned some representation for the digits, they trained. They had
Some classifier. Yeah.
Which assumes that
Think of
that's the
perceptron.
well, yeah.
Think of it as a perceptron.
And that works. That's what actually works.
Yeah,
for
for digits it works, yeah. This worked even back in the 80s and 90s. So Postal Service has been using automated tools for a long time. So Hinton proposes, and I'll give a little bit more detail about this generative viewpoint. But what's now causing some more discussion and controversy is that people are not convinced that these new ideas were that essential to begin with. That maybe even the 1980s backpropagation actually was pretty good. Okay, it's just that these days you have much more, a little bit better nonlinear optimization and much faster computers and parallel and so on. And even that does pretty well. So to confuse matters even further, Hinton himself at his Google, with his Google team, did an implementation of basically classic backpropagation with a few modern twists, but not very significant ones. Basically classical stuff. And that did pretty well. And I'll tell you roughly what it means to do well, just to give you an idea, okay, of the scale. So I think he had something like 600K nodes. So this is Hinton et al. In 2012. So this caused a lot of discussion, this paper. So 600K nodes and random starting point. They start with a random network. And actually, they use some other things too. For some layers, they have some other heuristic, not random. 600K nodes and just backpropagation. And let me tell you how they measure success. So what they did was they ran it on Flickr images, so millions of those. And some of them, many of them actually are also labeled, right, because somebody labels what they're about. So you have the image, and you produce some, this top layer is, to answer this earlier question, is it has, it's a classifier involving 2,500 terms, not classifier, vector, indicating indicating vector, whatever, the 0, 1 vector, indicating which of these terms are describing the image.
But what do you mean terms? These are just bits.
This is, yeah, these are bits, but there's a set of 2,500 descriptive words, river, mountain, whatever, and you can set, whichever of these bits to 1, depending on whether you think there's a mountain in the image. That's the intuitive meaning, okay? That's what these 2,500 terms mean. So I know that you have seen this thing in PCPs and so on lately, advantage over random. It's kind of funny. That's the notion that's used in evaluating this. So let's say, with one image, usually one term is probably not a good description. So let's say 5 terms, okay? So you take the 5 terms. So whole thing at the end must produce 5 terms to describe the image. And then the human is asked. And if the human's best term, what he says the most descriptive term, is one of these 5 terms, then it's a success.
So the terms are the 5 bits or the
5 bits. So there's a dictionary of 2,500 terms that they've decided.
So just give 5 bits for each image.
Yeah.
32 possibly different.
That's right. No. 2,500, choose 5.
So you have to choose the terms.
Yeah.
So and they mean something.
Yeah.
Okay. So you choose.
So that comes from the supervised part. Yeah.
something.
River, mountain, whatever. Yeah. Eiffel Tower. And Eiffel Tower is not one of the terms, but okay. So now let's see if it was a completely random guess, right? You're coming up with 5 terms, right? And the human supervisor is picking 1 term, and you have to match that. So your chance of success is 1 over 500, right, for a random one. So all the earlier attempts were, more like 5% success, okay, which is still quite an improvement over random, okay? A human supervisor.
No, the terms.
Oh, the terms. Oh, yeah, but that's part of the supervised layer. So you tell the circuit, we're trying to, after it learns the representation, right? We're trying to come up with these descriptive terms, okay, out of these 2,500.
But maybe the terms themselves are not that good.
So the people have thought about it a lot.
In the training, someone picked in advance 2,500 terms.
Yeah.
Then he does supervised learning with images in which everyone labeled those images.
Yeah. So you already had unsupervised, right? You did the net with unsupervised, and then then there's a supervised part where you train according to the terms.
Oh, I see.
Yeah. The human decides these are the important terms, and the circuit has to figure out how those maps to its internal.
The human looks only at the out.
Out.
Only at the out.
Yeah.
So all this is this 2,500 terms are probably maybe the network starts at
No, the human just says, I think 1 term describes this image, which is this, and the circuit backpropagation has to figure out how to adjust to that.
That's in training the model.
Yeah.
Yeah. But when you're done training the model, now they are going to
Yeah.
test success.
Right. The human just looks at 2,500 terms and picks 1. Yeah, for the image. Yeah.
He looks at the image and the dictionary of terms.
Yeah.
Not the circuit output.
Yeah. Okay. So this new paper of Hinton et al. Got 84%. This was quite a earthquake in this area.
84% of the choices were among the 5.
Yeah.
So
So
a human and another human, how much do they agree? So let's say
yeah, I don't know that number. Yeah, that's a good question. Yeah, you won't get 100% probably even with a human.
And was it the same set of humans that were doing the training? And
I
the
don't
set
know,
of humans
yeah.
that were doing testing?
I'm guessing they were using. Yeah, I don't know exactly how they picked.
But I mean,
Reliably
they
labeled
were
images.
really humans labeling for the
Yeah.
training, or they were just taking images with some bunch of text from a blog and just feeding everything?
I'm not sure. Yeah, I didn't check the methodology. They were reliably labeled in some way. Yeah.
isn't it all clear what this model is doing? Like, there's a function that goes from after it's trained, there's a function that goes from this input to the output. Can you at all see what this function is doing?
This thing.
Yeah, an arrow.
Very good question. So they had these pictures in the thing. They picked one of these 600,000 nodes, right? And pick it up and say this is its activation pattern, and of course it's going to be like nonsense, right? What sense will 1 of 600,000 nodes make?
It's not like wavelets where you can see.
Who knows? Yeah. Nobody knows. Yeah.
So is it like the same type of database, or so first there is the database that you train the
No, that's all standard methodology. So you reserve some, and it's not. There's no cheating here.
Yeah, there's random partition of the.
Yeah.
The new algorithms had all kinds of successes, like achieving
Yeah.
better results in computer vision.
Yeah. No, I'm not saying that this new stuff is all irrelevant. I think most of Hinton himself still writes in the think, this was just an experiment to see just what the classical ones do. We think that with modern techniques, you should do better.
So it justifiably looks amazing, right?
Yeah.
It is amazing. I think
Yeah.
it's amazing that
Yeah.
Something
like this.
that was trained like this produced.
Nonlinear optimization on 600,000 nodes.
No, what I was asking is whether the classical algorithms can achieve something that is.
Okay, guys, let's not.
Okay.
This is not the point of the talk. Any other quick questions about it so you understand? Okay, I'm not want to talk too much about the practical part. Okay, I just want to tell you something about it so that you have the context. Okay, so now, so what we're going to do is work in this generator model and learn the parameters of the distribution. Okay, so it's nonlinear, okay. So let me tell you what was this reversible part. Okay. So this is a notion by Bengio et al. Maybe 07 or something, soon after Hinton's work, which is a denoising autoencoder. So this is a notion involving a single layer network, where you have some visible layer H and a hidden layer. Sorry, a visible layer X and a hidden layer H. And there's some network in here, and we're defining that. Okay, what's the desirable property? And it's something like error correcting codes, but it's nonlinear. Okay, so and it's real valued. So you have an encoding function, decoding function, D, and you want the property. Did I erase it? I erased it. That the decoding of the encoding of x plus, oh, okay, I didn't define it. X plus noise is approximately equal to x. Okay, and in fact, the definition specifies a form of the encoding and decoding function. So encoding function of x is sigma applied to w of x plus b, and decoding function applied to h is sigma of w prime x plus b prime. So let me just draw this out.
There's no H in DLH.
Oh, sorry, H. Thank you. So what you have is, it's very reminiscent of neural nets. Okay, so you apply a linear function on this, right? The W is a matrix. These are matrices. So this is W1 times x. Over here you have W2 times x, etc. Right? These linear functions. And then on this vector, right, this is a vector, you apply a nonlinearity on each coordinate, nonlinear transformation. So threshold, let's say. Okay? So think of sigma as threshold. As threshold, meaning greater than or equal to 0. B. Just, yeah, a shifting. Each is a perceptron, yeah. Think of it as a threshold, yeah. Okay? So you can go from x to h using a perceptron, or level of perceptrons, and reverse. No, that you have to put constraints on, yeah.
When you see it's like you're also correcting codes, the noise comes before the encoding, right? So in error correcting codes, we
Yeah.
encoding, then
Yeah.
the noise
Yeah.
encoding. Here, the noise comes.
Yeah, that's right. It's more like, okay, so okay, let me, so we were actually confused which is encoding, which is decoding earlier. This is there, you know, you could call it either, right, which is encoding, which is decoding. So you and I would think of this as the encoding, right? And then this all makes sense. So,
But
but
anyway,
their terms are flipped.
These are parameters that you impose there.
Okay, so all right. So firstly, is the definition clear? So there's a thresholds to map from X, network of layer of thresholds to map from X to H, and then one going from H to X. Okay. Yeah. Your question was.
What do you
Okay.
impose to make it non-identity?
Non-identity. So for instance, you could say that this is you know, it's a sparse vector in a larger space, for instance.
So sparsely one that probably you have some distribution. This should probably hold on average in some sense.
Yeah, on the, over the samples, the sample distribution.
Yeah, which you know.
You're given samples from it.
Yeah, no, right.
You're given a sample.
You don't know the distribution, just given sample.
So you write an empirical thing. I erased it already. But yeah, you write all those things empirically in your nonlinear optimization. Yeah.
So the idea of D and applying DNE is to remove the noise so that the I'm just a little confused about the approximately equal. Should it be X plus some noise which is much smaller than the original noise?
Yeah. So just think of it as equal, okay?
So it's the denoising stuff.
It's denoising. Yeah. Okay. So in case you're wondering, you know, what are these things? So if you use, for those of you who know about compressed sensing, it's a linear version where the D is linear. Okay, so you just map, so you assume that somebody is mapping some unknown vector H to A times H, and then noise is added here, and H is sparse, and then noise is added here, and then you can go back, assuming you know A. Right? That's compressed sensing. Those who haven't seen it, don't worry about it. But okay. All right. So one intriguing thing that they use, which really floored me at some, early on, was that they use something called wait time, which means that W prime is W transpose. Okay, so what that means is that you look at this bipartite graph, right, with the weight function going from X to H. Use the same graph, okay, the same connectivity. So the same edges get used, and you compute a different threshold here.
That's what you would do if it was linear, if you didn't have the nonlinear.
Yeah.
So the weights W.
Avi, actually, that's not clear to me in general, but it's true for compressed sensing or something, under some conditions, yeah. That's what you would do.
It's natural.
It's natural, yeah. Uh-huh.
So the W's are the same, but the thresholds are different.
Thresholds can be different, yeah. Which you need also for compressed sensing, yeah.
Are you right control? I mean, it would seem that the natural thing to do would be to take the inverse.
Yeah,
but that's the whole point in compressed sensing, right? The W transpose is the approximate inverse.
if the matrix has strong properties,
Yes,
like
compressed
RIP
sensing.
or something
Yeah.
like this,
So, okay. So this was bizarre, and actually I quizzed them, why do you use this? And they just, the way they think of it is, this model is too general, right? It allows everything. So they're trying to constrain it. And this is a very powerful constraint. Okay, that's all, and they have some intuition why it makes sense. So actually you'll see, at least in our model, this is true. They don't specify. So there is training where you start with a complete matrix, and then you learn the weights. Okay, so after all this, I'm ready to. So okay, so using these denoising autoencoders, now you can see that you have a generator model, right? That you actually have multiple hidden layers, H1. Sorry, it starts from here. H1, H2, H3, H4, etc. And you have the input X. And if each layer is a denoising autoencoder, then it's sort of reversible. So you can use X to compute all these layers, and then you can reverse them. Okay. So you have a denoising autoencoder between every layer, every pair of layers.
So each one looks like this.
So it's like a denoising autoencoder. So the first example of this denoising autoencoder was by Hinton. It's the restricted Boltzmann machine, which is one of these physics concepts.
Okay,
But
so each of them is a linear part and threshold part, and
Yeah.
then we do it again and again.
Yeah. And different weights. Yeah, I mean,
Yeah,
And we specify how many.
and you can specify edges. Yes, you can put a sparsity constraint. Look, they have already thrown in nonlinear optimization. They can throw in anything they want.
How many layers?
Everything you can specify. Yeah.
so about the specification, I mean, when they had this wonderful success, I assume that they said that it didn't work with 400K nodes, or it didn't work with one layer less than they did. How many layers? I don't have no idea how many layers they have.
Yeah.
They probably try to use less so that they can learn it faster, it will be better, and so on. Or they don't mention it.
No, I think all of those are interesting. Yeah. And, I didn't study it so much. I don't remember. Certainly not all. A lot of this work is being done at Google. So it's a business secret. Yeah. I'm not sure if they are willing to give you too much detail. Like you certainly can't get the code to run that network. Okay, so so this is a generative model, right? So now we took the following approach. So suppose we assume that this top distribution is something nice, like a random k-sparse vector. Okay, and there's some ground truth here. We don't know what it is for our problem, right? For our distribution, there's some unknown ground truth. Okay, ground truth net. And yeah, if you run this, you get the initial distribution. And now you're given samples from the initial distribution, and then you're trying to learn this. Okay. That's the viewpoint. Okay, this is just completely traditional, right? Learning mixtures of Gaussians or whatever. There's a model for how the data was generated, and now you're trying to learn the parameters. Okay. I'm not saying people have thought about this. I mean, this is an obvious problem here, but because of nonlinearities and so on, people were kind of stuck on it. So, okay, so that's the viewpoint. Unknown ground truth net, some simple distribution on the top, and then this is a generative model that produces the input. And now we have to learn it. Okay? This ground truth.
The distribution, as you are trying to, so there is a fixed circle that you don't know. It defines, assuming the output is a random k vector, it defines the distribution on the input. You are getting samples from the correct distribution.
Yeah.
From the correct
Yeah,
distribution.
just like in mixtures of Gaussians and whatever, right? You assume that the distribution is, yeah. But in our setting, actually, we can get noisy samples and so on.
But you are assuming that this correct distribution on the right network is generating back
Yeah.
the forward direction.
Yes.
A random case path.
Yes. Which you can think of like in this example, right? These 2,500 terms. You can imagine that for every image, there's a random set. For the average image, there's a random set of 5 terms out of the 2,500. If this was a sufficiently compact set, that'll be true.
Does the algorithm to train know that it's supposed to be getting a k-sparse vector going out?
Yeah, you can throw that in. Sure, why not? I mean, we're doing nonlinear optimization. Not we, but these guys are doing nonlinear optimization. They can throw in any constraint that you like.
So, but in this sense, you're using what you want to get in the top to train it, right?
Oh, that's used throughout this whole methodology, as I've been emphasizing. You have to say how many layers. What's this nonlinear function? Some people use thresholds. Some people use other things. How sparse is this graph of weights? You can put a constraint there. How sparse is this intermediate representation? All of this is an art, and all of those are imposed in the real life training. Well, I'm saying there's a generative model, yeah. So we, but that's never a big deal, right? Because I can try 1 layer, 2 layer, 3 layer. You know, there's a constant number of layers.
Yeah, but
I can.
There's a clear, approximation theory question here, right? Like more layers,
Okay.
more approximation, overfitting.
Okay, good. So no, overfitting is, in our viewpoint, is never a problem because we just assume there's enough data.
More than okay.
Yeah, there's always a.
Number of layers, you get enough data. Right.
Yeah, so there's never a problem with overfitting. You learn the ground truth, arbitrarily close. What was the other question? But that answers your question. Yeah.
So the top distribution is a tuning parameter too. When you're
Yeah. In a real life training, it would be a true. Yeah. Okay. So here's what we do. So what we show. So okay. Let me just prepare you for the result. All these things. They're kind of like, as I said, error correcting codes, compressing things on. But there's a nonlinearity. Okay. So now we're in new territory, right, which has not been studied. So what's the first thing you would try to study in this case? No, linear is compressing things.
So just one layer, just the error correcting coding version of.
But is it real valued? Yeah, and it's nonlinear. Yeah. So but what would you study?
Just one of the, I don't know.
So what's the first error correcting code that people analyze? Gallagher or something?
Yeah, so the LTPC, yeah, but it's defined like that.
So
it's defined like that only without the thread.
So exactly. So we so our result finally. So this is joint work with Aditya Bhaskara, Rong Ge, and Tengyu Ma. Tengyu's over there. Is that if ground truth is a random neural net of certain degree, of degree n to the gamma, then we can learn it. So by random neural net, I mean that, so firstly, there's a degree constraint. So we assume that in the ground truth, these hidden features don't affect too many other features and are not affected by too many. So n to the gamma, okay?
So they're all the same length. The length of the.
And then the weights. You mean the weight? Oh,
length of the layers.
length. Oh, that's not so important. I'll come to that. Yeah. N to the gamma, and then the weights are random in -1, 1. Yeah, I'll return. I mean, we can handle other vectors, but those just boost up the sample complexity. So yeah, B is 0 actually. Okay, but that's a sort of headline result. So
can you state a theorem or something?
it is not a theorem.
Understand what this means. So if you start from something where you chose random sets, random uniform sets of size into the gamma, on each of them you put random weights uniformly times 1, 1.
Yeah.
And you compute the threshold.
In the generative case, yeah. So you start from so somebody, nature, starts from a random k-sparse vector here, passes it through this random network, gives you the sample over here. That's what you're given, and you have to learn the network.
And you want to learn,
You want to recover this?
one layer or many layers?
You mean in the ground truth? There are many layers, yeah, k layers.
Okay. And what is objective? What do you want to learn?
I want to learn the ground truth.
I want to learn the weights, and I want to learn the sets, and
Yeah.
I want to, and I don't know how many layers, or I have some, I know it's.
You know it. I mean, it's just a constant, so you can try 2, 3, 4, whatever, if need be.
By learning, you mean produce a distribution?
Yeah, which is indistinguishable, yeah. I mean, you produce a generator model which matches this. And if these weights are not real valued but discrete, like ±1, then we can actually learn the ground truth. If these weights are discrete, I mean, this is a general problem in all these things, that if the weight, if the unknown parameters are real valued, you can only get statistically, you can match statistically. But if these are discrete valued, then we can actually learn the ground truth.
So you learn only the function of the k-sparse vector, or then you can also recover all the k-sparse vectors for each of the samples you've seen?
Yeah, you can recover that. Yeah.
You can recover that?
Yeah. Oh, yeah. So, yeah, we'll also give you a way to compute backwards. Yeah. And it'll use this wait time. Okay, this is just the usual random graph model. You can use either, so you have a bipartite graph, okay, and each node here has degree d. And for simplicity, I'm assuming for this talk that both sides are of the same size, n, so degree d. Or you can use, d has to be bigger than log n, as you would imagine. And so, degree. So that the graph has nice properties. And so yeah, you can also use each edge with a certain probability. Any random graph model. That's the random weights -1, 1.
It's
Uniform.
So what is the relationship between gamma, k, and the depth?
Okay, so gamma is gamma is 1 over the depth. Less than equal to.
So you don't. This means that that's it, or there's a constant, big constant.
It's not a big constant. Okay. I'm trying to remember if there's a 1.1 or something, but yeah.
Yeah. So the point is
No, it's roughly that.
And
K is what? What is K?
Yeah,
Number of levels?
Sparsity at the input.
Yeah. I see. Right. Right. So let me write this. So gamma is less than or equal to 1 over depth. Okay. So this. Okay. So now you want the. So there's two versions. Okay. Version 1. Bottom. The x is somewhat sparse. Yeah, you're exactly right. Somewhat sparse. But 0, 1. So this means something like 1 over log n or something. So we can even make it maybe 1 over log n, but we can't make it constant.
So in order for this to be true, the k has to be pretty small, right?
Yeah. So this means that k is n to the minus gamma something. N to the minus 1 over the n to the 1 over the number of levels or something like that. Or something like that. Yeah.
You don't otherwise.
Yeah.
K is
K is
the number of ones.
the number of ones. Yeah. So.
One minus this. Yeah.
No, the number of ones is this. Number of ones is n to the 1 over. Yeah. Yeah.
So DB sequels are linear codes. So what do? You adapt them to be nonlinear? You said you use LDB sequels?
We don't use LDB. It's a random. I told you it's a random ground. We don't use it. It's just inspired by it. Yeah. I would just mention that as an analogy, right? That people first understand. Version 2 is that x is not sparse, but real value. Okay, and then in this last level of the generative model, there's no threshold. So you just get the sums. So bottom level has no thresholds, only sum. So decoder is linear.
How do you choose the thresholds?
Okay, so thresholds are all, so the thresholds determine the sample complexity. So we are assuming that the threshold B is actually 0.
Even in the sparse case?
Yeah, both cases, yeah. Well, in this case, yeah, both cases. So you can use version 1 if you assume that somehow somebody has done a hand coding so that you can get from, say, images to some sparse representation to begin with. And then you can, that's your real data. Okay? Or you can assume that there is some raw real value data here, and then the bottom layer is just this random linear decoder.
So I'm sure you will tell us at least something about how to prove something like this.
Yeah. Although I'm out of time already, huh?
No, we give you more time. We stop you all the time. What I'm wondering is how related do you think this model is, the random network model, to a model which captures images?
Okay. So should we table that until the end, maybe? Yeah. Yeah, because this is a theory talk. I've already done much more practice here than in the rest of the talks this year, right? So, anything else? Yeah.
Why is it so important for the network to be random?
For our result, we use it all over the place. Yeah. I mean, if you've seen the analysis of any of these things, compressed sensing or LDPC codes or whatever, it's much easier for random.
Yeah, I mean, usually there will be a property or a few properties
of random graphs
that you can articulate that out. Yeah, you don't really need random.
Oh yeah, but it's more than expansion. Yeah.
So basically, what you say is that you can learn random neural nets.
Yeah. So measure one. Yeah. In this model with sparse interconnections, which actually they don't seem to mind. Yeah. So okay. So yeah, in the typical neural nets they have. Actually, I'm going back to a little bit of your question. They have some hand-coded layers using some pre-processing, which they understand. The low-level processing, and then the high-level processing they don't understand. Low-level is like wavelets, blah blah blah, and then the high-level they don't understand. And there they just train a complete graph, 4 levels. So it's like that. Yeah.
So Sanjeev, I have a question about the case 1 n to the 1 over a number of levels.
Yeah.
So if we had just one layer in linear encoder, we would expect almost n, right?
Yeah.
K, n over log.
Yeah, that's the last layer.
And so
in this.
do you think if I told you what the network was, like I tell you exactly what it is.
Yeah.
But it's just all these nonlinearities.
Yeah.
Do you think there would be also a decay? I mean, do you think this is like?
Yeah. The problem is the learning. Yeah.
Oh, it's in the learning.
Yeah.
If you gave me what the parameters of
Yeah.
the network were, you could actually go all the way to k almost n.
Yeah. I mean, compressed sensing does it. Right?
So when you say you can learn it, are you using the same algorithm as what Hinton used?
No.
It's
Completely different.
But similar model, like under your assumption.
Yeah, completely different algorithm. I would argue that actually it does what they should be doing a little bit more. Instead of doing gradient descent, which is a very local thing, they should be doing something more global, and you'll see. Any other questions? Okay, so let me give you a 15-minute introduction to the algorithm. Okay, for theorists, I don't think there's a whole lot of surprises. Okay, once you think about it the right way. So let's focus on learning one layer. By the way, first let's see why a random net is a denoising autoencoder. Okay, so again, this will remind you of error correcting codes, compressed sensing, etc. So the reason is that a random deregular graph is an expander, high expander. And so if you have a set here of size, so let's say it's degree d, and you have a set here of size, let's say n over 10d or something, okay, that's the number of ones in the previous layer. Well, then what happens is that there's this unique neighbor property. So for most of these d neighbors of this node, let's say more than half of them are neighbors only to this node, not to the others. Okay? And then for all the other nodes outside this set, the number of neighbors they have among this set is less than, say, 1/4 or something. Okay? So now if you know the network, if you want to go back from this, all you do is you take all these neighbors of this node, apply a threshold to see if more than d over 2 of them are 1 or whatever, and then that gives you this value. It's just from expansion. Okay? And now the weights and so on don't make a difference. Okay, if some weights are negative, some are positive, the negative ones will be all 0, but the positive ones will give you still the threshold property. Okay? Was that too quick? Ask a question. Okay, so that's why it's a so the main part is learning. Okay, how do you learn this from samples? So learning a single layer. By the way, this is what the applied work does. Okay, the unsupervised learning, you train layer by layer. So you use the data to learn the first layer, which is the data for the next layer, and you learn that, and so on. So learning a single layer. And I'm not going to talk about this, with the real value thing. So I won't talk. It's a similar intuition, but I'll just talk about this. So you have a single layer, and there's some assignment here, which is row n ones. And the others are 0. And that produces some assignment here. And the assignment that's produced here is you take the sum, weighted sum of all these values of the neighbors, and if it's bigger than 0, you output 1. Right? So it's just two simple conceptual parts. The first part is, suppose I give you the following task. Given any two nodes u and v, tell me, are they connected to the same node on the previous layer? Okay. So task 1, identify all node pairs uv on layer 2 or lower layer 2 that are connected to the same node on layer 1. N by n, yeah, let's say n, yeah. D. So we are assuming that rho n times d is less than n.
And of course, to learn the pairs connections, it would have been sufficient to learn the singletons connection.
In a random graph.
Well, no, in any graph, if you knew all the connections, you would know about the pairs. The point is that you will not get this information for all pairs, but you will get for enough.
No, we can get it for all pairs, actually. We can get it for all pairs with high probability. The point is that, yeah, so suppose I tell you that u and v are connected to the same node, right? Well,
to the same node, but not which node.
Yeah, I don't tell you which one. Yeah. Of course, I don't know which one.
What we want to know is whether for each pair they have a node in common.
Yeah. Okay.
For some parameters, the answer will be yes. Yeah. For all u and v and for all, right? Because if the degrees are more than square root n, then I would every pair would have.
Yeah. D is less than square root n. D has to be less than square root n.
So D is pretty small because before you said 1 over the D.
No, D over gamma, n to the gamma is
the degree is n to the 1 over the number of values, which is less than n to the, actually even 0.4. We need that. Indeed. Otherwise, you get a complete graph. Yeah, all pairs are. Okay, so you do that. So I'll describe in a second. And then task 2 is use result of task 1 to learn all edges. Okay. So now, actually, all it is, they're connected to the same node on layer 1 via a positive edge. Okay, that's what we'll do. And that's enough, via a positive edge. Okay, so that's the conceptual. So let's see what task 1 is. Again, it'll be a sketchy proof, but I think you'll see the idea. The point is that suppose two nodes are not, so let's first see what's their correlation. So we look at this quantity. Probability u is 1 and v is 1. Okay? If they are adjacent to the same node here, this probability is at least rho. Oh, I'm assuming that it's for a single layer that this is a random set of rho n. Now in a multi-layer that won't be true, but for now there's a random set of rho n nodes that are 1.
So rho n is rho times n?
Rho times n.
But I thought you had subpoint.
This is just, huh?
I thought you started with a subpoint.
That's at the top level. Right now I'm some intermediate layer, and for simplicity I'm assuming that this assignment is a random. It's not random in a multi-layer thing. For now I'm assuming it is.
Okay. And you assume there's a linear number of ones.
Rho times n. Rho is not linear. No. Rho is not linear. Yeah. Rho times d is less than 1. Rho times d is less than 1. Okay. So now let's look at this. So if they have a common neighbor here, this will be 1 with probability with positive. This will be 1 with probability rho. And then there's a reasonable chance that both of these will be unique neighbors. So they'll be 1 as well. Okay? So this is say bigger than, let's say, at least rho over 2. Okay? If UV have a common neighbor. With positive edges to that. Is this clear? I'll say that again quickly. I'm saying if they have a common neighbor, then they are kind of correlated, because with probability rho, this neighbor is 1, and then when he's 1, because he has positive edges here, and there's some good probability that this will be a unique neighbor, so there's no other neighbors of this which have any, which are 1s, and so therefore this will turn on, right, because there's a positive stimulus coming in, and so it'll turn on, and same for this. Okay, so I'd say with rho over 2 probability, they'll both turn on. Okay. Now suppose they don't have a common neighbor. So then he has some d nodes here and some d nodes here. And so it'll be rho d square, roughly. Okay. And so our parameters will be such that this is less than that. Okay. I'm giving you a simple version of the algorithm using pairwise correlations. You can analyze higher order correlations and get better parameters, but for now just assume this is less than that. Okay? So what is rho d? Rho d is the output density. So the output density square is less than the input density. Okay, so that test identifies this. So now what you can do is, so actually you don't learn all the edges, you learn all the positive edges first. So let's see why that is. Okay, so this is obscure paper I wrote when Grant was a postdoc here about community finding, and then turned out this is exactly that problem, and this is actually a very I think important problem in this setting. So community finding is, in a nutshell, is you have a social network like Facebook or something. You are given pairwise, which pair of people are friends. And you're trying to find communities. Okay, your high school community or whatever, college or whatever. And the point is those communities are overlapping. Okay, so the traditional large body of work on this assumes that communities are disjoint, implicitly or explicitly, and we want it overlapping. So anyway, turns out this was exactly the problem we're looking at, but it's much easier because the graph is random. So okay, so it's just almost 2 lines. So now I'm given, so let's see. So which are the nodes that that have a common neighbor? So this is U. Which are the nodes that have a common neighbor? So take any of its d neighbors, and then each of those has d, right? So it's d square other nodes. Okay, so this process will yield for every u, it'll give you something like d square other v's. And now you're trying to find which of these v's are actually adjacent to the same, to this node. Okay, the identity of this node doesn't matter, right? It's just a number from 1 to n. So we'll just find clusters. And that's very easy, because if you look at all the nodes that are adjacent to the same node, they'll also have edges to each other, right, in this process. They'll be identified as valid pairs in this process. But most of them will not be identified, so this U has something like d square other vertices which have a common neighbor with U. But then if you want to just identify like the common neighbors to this node, what you do is you pick a random one of these other d square nodes, let's say this one, and now you're trying to identify other of that, right? And that's just exactly the set of to a first approximation will be the set of nodes that are identified as pairs with both of these. Okay? No, guys. Okay. So right. So we identify all pairs of nodes which have a common neighbor. Okay. So now pick a. So here's the algorithm. The n communities. In n communities, yeah. Yeah. And what we're saying is, take a random node that you identified as a pair of U. Okay, in that process. Let's say it's this one. Now, what are the other nodes that are adjacent to this same node? They are basically the ones that were identified as pairs with both this and with this.
Another way of thinking about it is take n random pairs of nodes and then take their common neighborhoods.
Yeah. Yeah. There'll be a little bit of noise, and which you can remove. Okay.
From a square of a random matrix, you can identify the matrix.
Yes. So it's a graph square root kind of problem, right? Which in general is NP hard, but for random graphs, sparse graphs, it's easy. Yeah. Or random like would work too.
Another thing I didn't understand. So this is single layer, but you don't have access, right? So you have input and output after all the.
We have this layer. I have this layer. I have samples from here.
So you have samples from the middle or something.
So that's the layer wise. So this is the layer wise idea. You take the samples at the bottom to learn the next layer, which you use as samples for the next layer, and so on. That's what we do. Okay. So I'm assuming by induction that I have samples here, and I'm learning this. Okay. So now the only thing I have to describe to you. Okay. So that's only takes out the positive nodes. There's a little bit more work to identify the negative nodes, because negative nodes, negative edges, I mean, because those are inhibitory, but those can be identified too. And then I have to show to you how this works in a multi-layer setting. Okay, so in a multi-layer setting, this assumption is not true, right? That this assignment is a random assignment, because there will be some correlations, obviously. But the point is that these correlations arise because of common neighbors, common ancestors somewhere up. So maybe two nodes don't have a common neighbor here, but one of these nodes has a common neighbor. Because if this is 1, if there's a common neighbor and it's 1, then both of these nodes become quite likely to be 1, because this feed-forward process will make them 1 with good probability. So then you have to identify, you have to do a calculation of how many common neighbors and so on. And let me just give you the 1-line or 2-line summary of that calculation. The idea is that the number of, so it turns out the interesting ones are the positive edges, and for building up correlation. And so the number of, if you go up I levels, the number of ancestors is d over 2 to the I of every node U and V. And now you're trying to understand the correlation that could arise, because they could intersect. And but the point is that correlation also drops out geometrically, because the density here is also, if the density over here is rho over d over 2 to the I, if you do a calculation. I mean, this is why the top density was pretty small. So the density is dropping as well, and the number of potential common ancestors is increasing geometrically. but the two kind of cancel out. So there's not a lot of correlation. So indeed, this assumption is relatively okay, up to a constant factor. So that's it.
So for this, you will need that rho n times d to the I is less than n. So I mean, this condition.
This is anyway true, right? Because we start with something sparsing at the top, and we're assuming that the bottom layer is still sort of sparse in the 0, 1 case.
So mathematically, you would assume that rho times d to the I,
which is true, which is true, which is true. That's why the last layer is sparse. Yeah. That's where the last layer has to be sparse.
Okay, so first, thanks. And now question.
So the statement is not just that, it's not that at every layer you're proving that the distribution is close to some uniform distribution over case sparse. You're just saying that you're controlling correlations over some.
That's all we need, yeah. But the corollary is that too.